Welcome to Chemistry in the Kitchen! Today on Chemistry in the Kitchen, we'll be talking about acids and bases,
an effective nuclear charge,
and polar and non-polar solvents.
On today's segment of Chemistry in the Kitchen, we'll be talking about acids and bases. Here we have some lemon and limes with a pH of 2, making them acidic. While here we have water with a pH of 7, meaning that it's neutral. Here we have some bleach with a pH of 13.5, soap with a pH of 10, and baking powder with a pH of 9, meaning that they're basic. pH is the measure of hydrogen ions in the respective solutions.
In case you were wondering, the 6 strong acids include hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid.
In case you are wondering, strong bases include first group 1 metals except for hydrogen, and group 2 metals except for beryllium and magnesium.
Next on Chemistry in the Kitchen, we'll talk about effective nuclear charge. Effective nuclear charge is the force of attraction between the outermost electrons and the nucleus. I'll be modeling this with the aluminum atom. So this is the nucleus of the aluminum atom, and I'm going to be putting in the electrons with these chocolate chips. So these are the first shell, which has 2, and then the next shell, which has 8. 1, 2, 3, 4, 5, 6, 8. Cool. And then the very last shell, which has 3. These 3 electrons on the end are called valence electrons because they're on the outermost shell and they transfer when a compound is created. To calculate effective nuclear charge, you subtract the 13 protons, which are in the nucleus of the atom, from the 10 core electrons, which don't count the 3 valence electrons, and you get the overall charge that each valence electron sees. And in this case, for aluminum, it would be 3. So each of the valence electrons would have a pole of +3 from the nucleus.
Have you ever wondered why your oily hands are still oily even after you've washed them with water? Well, that's because water is a polar molecule, which means that it's positively charged on one end and negatively charged on the other, while oil is a non-polar molecule, which means it has no net charge. So since positives are attracted to negatives, the positive end of a water molecule will pull on the negative end of another molecule, resulting in the dissolving of that molecule. Then a spoon, maybe. So we can demonstrate this by putting some oil in water. And as you can see, all the oil has risen to the top. And even when I stir it, the oil and water will still not mix and the oil will remain at the top.
Hey guys, I'm going to show you one last awesome milk trick that occurs when you mix milk, food coloring, and soap together. There's a cool reaction that occurs when that happens, and I'll show you guys right now. So, as you can see, if I add in the soap, cool artistic variations occur. And this is because the food coloring is less dense than the milk itself, and the food coloring remains suspended with the milk molecules. And as when you add in the soap, this brings up the fat from the milk, which henceforth brings up the food coloring, and it creates these cool mixtures.
Today on Chemistry, today. Alright.
Which have a pH of 2 and are acidic in nature.
Oh, that was okay. Come on, Sarah. A little more arm.
Oh no.
And effective nuclear charge. Stop!
Wait, I have an idea.
Yeah.
Alright, go for it.
Alright. Give me a second. Hold on.
It's been recording.
Oh, good. Ooh, Maria.
Aw.
Guys, I am killing the making. I'm gonna literally go home and use all the food coloring to make this.